So moving on with our discussion of RC circuits, so these are circuits with capacitors in them. Let's think about what would happen if we put a resistor in the circuits, which is what we have been doing, if that actually changes anything. So you could have a light bulb with a thin filament, or you could have a light bulb with a thick filament. So make it really nice and thick. All right, so this is going to have more resistance than this one. And will this impact our capacitor circuits? So the end result is that no matter whether you're discharging from a capacitor or charging up the capacitor, you end with the light bulb going out. So we know that the thin filament will be a little bit dimmer, requires lower current, and takes a long time. And this is going to burn a little bit brighter. It's going to require higher current, and this is for the battery being hooked up. You'll see once we get to the circuit equations why this requires higher current, and it will go out faster. But would any of this impact the charge of the capacitor? Well, no, this does not. Capacitor charging. Because either way, you end with the final state of no current. And then in the final state, the only potential difference are across the battery and the capacitor. And it would make sense, these are equal to each other. So basically, the bulb makes no difference. The bulb or resistor makes no difference. To the final state. All right, so let's look at a couple other capacitor circuits. So you could have two batteries connected, and then you could have capacitors in parallel. So this is where the current branches off into two different paths and they connect back together. Then you can have a little light bulb here, why not? And so for this circuit, the capacitors are in parallel. And this will essentially act as one capacitor with double the area. And the result of that is the bulb glows twice as long, assuming the capacitors are, the same. And then you could also have a circuit, again with your batteries. And in this circuit, the bulb is isolated from the batteries. And what will happen is the bulb still glows because the electrons still move. Or you could have a circuit, and this is a circuit which actually shows you how capacitors are most commonly used. You can have a battery here. And in this case, you've got a capacitor here, so it will charge up, and then this current will still be allowed to flow. This essentially will become a dead end. And what will happen is that if one of the batteries goes out, then this current will still continue to flow by discharging the capacitor. And that gives you time to replace a battery. So RC cars have circuits like this. And RC circuits like this are really common, and you can see why. There's some really practical reasons. So this is a common RC resistor capacitor circuit. So a few other things. So in the charging time, do the following: gain or lose energy. Bulb? Not really, no change. It goes from, remember, this is over the entire time. It goes from off to off. Battery. Well, that's going to lose energy because it's going to, yeah, that's how batteries work, is they slowly deplete of energy. What about the capacitor? This gains the energy. All right, so when you've got an RC circuit, let's look at what happens with our current node rule. So we know that if you've got your I coming in, it's going to be equal to all the I going out. Sum of I entering would be I1 minus I2 minus I3 minus I4 is equal to 0. Very familiar with this rule at this point. All right, so let's look at something that would be a little more interesting. So if you've got current coming into the capacitor, and then you've got current leaving. So 1 and 2 are nodes. And let's look at what's happening there. So 1, while charging, current is coming on to the plate, but not off. And at location 2, current comes off, but is not replenished. So this is not a steady state, which you already know. However, if we look away from the capacitor, just as much current in a short time period is leaving one plate as is coming on the other. I mean, we do have a quasi-steady state. So you can still use current node rule elsewhere in the circuit, just not on the plates. And of course, you need to look at a small chunk of time because the current is gradually changing. So node rule still works, just not with plates. So all of this leads me to something called capacitance. So if you have your plates with area A, you've got your electric field pointing towards the -1, some separation here. So we know the larger the magnitude of the charge, the larger the magnitude of the electric field, and the larger the delta V. So these all have a one-to-one relationship. So from here, we see that delta V is proportional to the charge. And this leads me to the definition of capacitance, which is you've been looking at capacitors if you've been ahead in your labs, and you've seen that they have something on them, which is their capacitance. So charge is equal to C, which is capacitance, times the magnitude of delta V. And the units are coulombs per volt or farads. Okay, so let's play around with this. E in the gaps, which is perfectly fine, it's not like the God in the gaps argument, is E is equal to Q over A over epsilon naught. Thus, delta V is equal to Q over A over epsilon naught times S. Okay, so there that is. Let's keep playing. So we're going to use, so we've got the delta V is equal to Q A epsilon naught S, and we're going to use that delta V is also equal to E C. Therefore, C is equal to Q over delta V, which is equal to epsilon naught times A over S for a parallel plate capacitor. And just a note, capacitance depends on the geometry of the plates. But if you want to do more complicated stuff, then you would take a more advanced circuitry class, which is more of an engineering type class to take. All right, this wraps up 19.1.